In an electrical distribution system, understanding short-circuit current ratings and breaker requirements is crucial for safety and proper operation. Let's consider a main distribution panel and a subpanel to illustrate these concepts. Firstly, the main distribution panel will have a main breaker. This main breaker must be rated for the available short-circuit current at that panel. In the example, if the available short-circuit current at the main panel is 40,000 amps, the main breaker must have a rating of at least 40,000 amps. The branch breakers in the main panel are generally considered protected by the main circuit breaker. This means that the branch breakers do not necessarily need to be rated for the full 40,000 amps. However, there are exceptions to this rule. For instance, if a branch circuit is supplying loads with a high surge current, such as large motors or transformers, the branch breaker might need a higher interrupting rating to handle the inrush current without tripping unnecessarily or being damaged. Also, local electrical codes or specific application requirements might dictate higher interrupting ratings for branch breakers in certain situations. Secondly, let's examine the subpanel. When the subpanel has a main breaker, the main breaker in the subpanel must be rated for the available short-circuit current at that subpanel. If the available short-circuit current at the subpanel is 20,000 amps, the subpanel's main breaker should be rated for at least 20,000 amps. Similar to the main panel, the branch breakers in the subpanel are typically considered protected by the main breaker. Again, there could be exceptions based on specific load characteristics or code requirements. Now, consider a situation where the subpanel is a main lug-only panel, meaning it does not have a main breaker. In this case, the branch breakers in the main lug-only subpanel must be rated for the full available short-circuit current at the main distribution panel. This is because there is no main breaker in the subpanel to provide additional protection or current limitation. Therefore, the branch breakers must be capable of interrupting the full 40,000 amps that could potentially be available at the main distribution panel. The justification for these rating requirements lies in the fundamental purpose of a circuit breaker, which is to interrupt fault currents and protect downstream equipment from damage. A fault current, such as a short circuit, can be several times higher than the normal operating current of a circuit. If a circuit breaker is not rated to interrupt the available fault current, it could fail to clear the fault, leading to equipment damage, fire hazards, or even electrical shock. In a typical electrical distribution system, the available short-circuit current decreases as it flows through downstream protective devices such as main breakers and branch breakers. This is due to the impedance of the conductors and other components in the circuit, which limits the amount of current that can flow during a fault. Therefore, the protective device at each level of the distribution system must be rated for the available short-circuit current at that location to ensure reliable operation and protection. For example, the main breaker in the main panel protects the entire downstream distribution system, so it must be rated for the highest available fault current. The subpanel main breaker, if present, protects the subpanel and its branch circuits, so it must be rated for the available fault current at the subpanel. And in the case of a main lug-only subpanel, the branch breakers must provide the necessary protection since there is no main breaker. To determine the appropriate short-circuit current ratings for circuit breakers, it is essential to perform a short-circuit study. A short-circuit study is an engineering analysis that calculates the magnitude of fault currents at various points in an electrical system. The study takes into account the impedance of the utility power source, transformers, conductors, and other equipment to determine the available fault current at each panel and device. The results of the short-circuit study are then used to select circuit breakers with appropriate interrupting ratings. The interrupting rating of a circuit breaker is the maximum fault current that the breaker can safely interrupt without being damaged or causing a hazard. Circuit breakers are typically marked with their interrupting rating in amps. It is crucial to select circuit breakers with interrupting ratings that are equal to or greater than the calculated available short-circuit current at their location. Using circuit breakers with inadequate interrupting ratings can have serious consequences. During a fault, the breaker might fail to clear the fault, leading to equipment damage, fire, or electrical shock. Additionally, the breaker itself could be damaged or destroyed, creating a potential safety hazard. In addition to the interrupting rating, it is also important to consider the voltage rating of the circuit breaker. The voltage rating of the breaker must be equal to or greater than the system voltage. Using a breaker with an inadequate voltage rating can also lead to failure and safety hazards. Electrical codes, such as the National Electrical Code, or NEC, provide detailed requirements for selecting and installing circuit breakers. These codes specify the minimum interrupting ratings and other requirements for circuit breakers in various applications. It is essential to comply with all applicable codes and standards to ensure the safety and reliability of the electrical system. In summary, understanding short-circuit current ratings and breaker requirements is crucial for electrical safety. The main breaker in the main panel must be rated for the available short-circuit current in that panel. The branch breakers in the main panel are generally considered protected by the main circuit breaker, but exceptions exist. The main breaker in the subpanel, if present, must be rated for the available short-circuit current at that panel, and the branch breakers are typically protected by the main breaker. In the case of a main log-only subpanel, the branch breakers must be rated for the full available short-circuit current at the main distribution panel. Performing a short-circuit study is essential for determining the appropriate breaker ratings, and compliance with electrical codes is mandatory. Remember that the purpose of a circuit breaker is to protect equipment and personnel from the hazards of fault currents, so selecting and installing the correct breakers is a critical aspect of electrical system design and maintenance. Now let's delve a bit deeper into some specific aspects of short-circuit current calculations and breaker selection. When performing a short-circuit study, several factors need to be taken into account. These include the utility source impedance, transformer impedances, conductor impedances, and motor contributions. The utility source impedance represents the impedance of the power company's distribution system. This impedance limits the amount of current that the utility can deliver during a fault. Transformer impedances also play a significant role in limiting fault currents. The impedance of a transformer is typically expressed as a percentage of its kilovolt-ampere rating. Conductor impedances depend on the length, size, and type of conductors used in the electrical system. Longer and smaller conductors have higher impedances, which can help to reduce fault currents. Motor contributions refer to the current that motors can supply during a fault. When a fault occurs, motors can act as generators and feed current back into the system. This motor contribution can increase the magnitude of the fault current and must be considered in the short-circuit study. There are several methods for calculating short-circuit currents, including the point-to-point method and the impedance method. The point-to-point method is a simplified approach that can be used for basic calculations. The impedance method is more accurate and can be used for complex systems. Computer software is often used to perform short-circuit studies, as it can handle the complex calculations and large amounts of data involved. Some popular software programs for short-circuit studies include EasyPower, SKM Power Tools, and ETAP. When selecting circuit breakers, it is important to consider not only the interrupting rating but also other factors such as the voltage rating, current rating, and trip characteristics. The voltage rating of the breaker must be equal to or greater than the system voltage. The current rating of the breaker should be selected based on the load that it will be protecting. The trip characteristics of the breaker determine how quickly it will trip under different fault conditions. There are several types of circuit breakers available, including thermal-magnetic breakers, instantaneous trip breakers, and electronic trip breakers. Thermal-magnetic breakers are the most common type and use a combination of thermal and magnetic elements to trip the breaker. Instantaneous trip breakers trip very quickly under high fault currents and are often used for protecting sensitive electronic equipment. Electronic trip breakers use electronic circuitry to provide more precise and adjustable trip characteristics. In addition to circuit breakers, fuses can also be used for overcurrent protection. Fuses are one-time devices that melt and interrupt the circuit when a fault occurs. Fuses have several advantages over circuit breakers, including low cost and higher interrupting ratings. However, fuses must be replaced after each operation, while circuit breakers can be reset. Some common types of fuses include cartridge fuses, plug fuses, and blade fuses. Coordination is an important aspect of overcurrent protection. Coordination refers to the selection and arrangement of protective devices to ensure that the device closest to the fault trips first, minimizing the impact on the rest of the system. Proper coordination can improve system reliability and prevent unnecessary outages. Coordination studies are often performed to determine the optimal settings for circuit breakers and fuses. These studies take into account the characteristics of the protective devices and the loads that they are protecting. Selective coordination is a type of coordination where only the device closest to the fault trips while all other upstream devices remain closed. This is the ideal scenario, as it minimizes the extent of the outage. However, achieving selective coordination can be challenging, especially in complex systems. Zone-selective interlocking is a technique that can be used to improve coordination. With zone-selective interlocking, protective devices communicate with each other to determine which device is closest to the fault. The device closest to the fault then trips, while the other devices are blocked from tripping. This can help to achieve selective coordination and minimize outages. Finally, it is important to note that electrical codes and standards are constantly evolving. It is essential to stay up to date on the latest requirements to ensure the safety and compliance of electrical systems. Regularly review and update your knowledge of the National Electrical Code and other applicable standards. Attend training courses and seminars to learn about new technologies and best practices. Consult with qualified electrical engineers and contractors to ensure that your electrical systems are properly designed, installed, and maintained. By following these guidelines, you can help to prevent electrical accidents and ensure the reliable operation of your electrical systems. Remember, electrical safety is everyone's responsibility. Never attempt to work on electrical equipment unless you are qualified and authorized to do so. Always follow safe work practices and use appropriate personal protective equipment. If you are unsure about anything, consult with a qualified professional. By taking these precautions, you can help to create a safe and productive work environment. Let's also touch upon the practical aspects of inspecting and maintaining circuit breakers. Regular inspection and maintenance of circuit breakers are essential to ensure their proper functioning and reliability. A visual inspection of circuit breakers should be performed periodically to check for any signs of damage, overheating, or corrosion. Look for cracks, discoloration, or other abnormalities in the breaker housing. Check the breaker terminals for tightness and corrosion. Ensure that the breaker is properly labeled and identified. Testing of circuit breakers should also be performed regularly to verify their trip characteristics. There are several methods for testing circuit breakers, including primary injection testing and secondary injection testing. Primary injection testing involves injecting a high current directly into the breaker to verify its tripping time and interrupting capacity. Secondary injection testing involves injecting a signal into the breaker's electronic trip unit to simulate a fault condition. The test results should be compared to the manufacturer's specifications to ensure that the breaker is operating within acceptable limits. If a circuit breaker fails to pass the testing, it should be replaced or repaired immediately. Proper maintenance of circuit breakers includes cleaning, lubricating, and tightening connections. Dust and dirt can accumulate on circuit breakers and interfere with their operation. Use a vacuum cleaner or compressed air to remove any debris from the breaker housing and terminals. Lubricate the moving parts of the breaker with a suitable lubricant to ensure smooth operation. Tighten all connections to the proper torque specifications to prevent loose connections and overheating. Keeping detailed records of all inspections, testing, and maintenance activities is also important. These records can be used to track the performance of circuit breakers over time and identify potential problems before they become serious. The records should include the date of the inspection, the results of the testing, any repairs or replacements that were performed, and the name of the person who performed the work. Furthermore, consider the impact of harmonics on circuit breakers and electrical systems. Harmonics are unwanted currents and voltages that can distort the sinusoidal waveform of the electrical power supply. These harmonics can be generated by nonlinear loads such as electronic equipment, variable frequency drives, and LED lighting. Harmonics can cause a variety of problems in electrical systems, including overheating of equipment, increased energy losses, and malfunction of electronic devices. Circuit breakers can be affected by harmonics, as the harmonic currents can increase the breaker's operating temperature and reduce its lifespan. To mitigate the effects of harmonics, harmonic filters can be installed. Harmonic filters are devices that block or reduce the flow of harmonic current. There are several types of harmonic filters available, including passive filters and active filters. Passive filters use capacitors and inductors to create a resonant circuit that blocks harmonic currents. Active filters use electronic components to actively cancel out harmonic currents. Selecting the appropriate harmonic filter depends on the characteristics of the harmonic currents and the requirements of the electrical system. Regular monitoring of harmonic levels in electrical systems is also important. Harmonic levels can be measured using a harmonic analyzer. If harmonic levels are found to be excessive, corrective action should be taken to reduce the harmonics. Remember that addressing harmonics is a crucial aspect of maintaining a healthy and efficient electrical system. Another important aspect to consider is the impact of transient voltage surges on circuit breakers and electrical systems. Transient voltage surges are short-duration, high-voltage spikes that can occur on electrical power systems. These surges can be caused by lightning strikes, switching of electrical equipment, or other disturbances. Transient voltage surges can damage or destroy electronic equipment, including circuit breakers. To protect against transient voltage surges, surge protective devices, or SPDs, can be installed. SPD are devices that divert surge current away from sensitive equipment, protecting it from damage. SPD are typically installed at the service entrance of a building or at individual pieces of equipment. There are several types of SPD available, including metal oxide varistors, or MOVs, and silicon avalanche diodes, or SADs. MOV are the most common type of SPD and are relatively inexpensive. SAD are more expensive but offer better performance and longer lifespan. Selecting the appropriate SPD depends on the voltage level, surge current capacity, and protection requirements of the electrical system. Regular testing of SPD is also important to ensure that they are functioning properly. SPD can degrade over time due to repeated exposure to surge currents. If an SPD fails, it should be replaced immediately. By installing and maintaining SPD, you can protect your electrical equipment from the damaging effects of transient voltage surges. Now let's talk about arc flash hazards and safety measures. Arc flash is a dangerous phenomenon that can occur when a short circuit or other electrical fault creates an electric arc. An arc flash can generate extremely high temperatures, intense light, and a pressure wave that can cause serious injuries or even death. Workers who are near an arc flash can be burned, blinded, or suffer other severe injuries. To protect workers from arc flash hazards, it is essential to implement arc flash safety measures. Arc flash safety measures include performing an arc flash hazard analysis, using appropriate personal protective equipment, or PPE, and following safe work practices. An arc flash hazard analysis is a study that determines the potential arc flash hazards at a specific location. The analysis calculates the incident energy, which is the amount of energy that a worker could be exposed to during an arc flash. The incident energy is used to select the appropriate PPE. PPE for arc flash protection includes arc-rated clothing, gloves, face shields, and helmets. The PPE must be rated to withstand the calculated incident energy. Safe work practices include de-energizing equipment before working on it, using insulated tools, and maintaining a safe working distance. Always follow lockout-tagout procedures to ensure that the equipment is properly de-energized before work begins. Training is also an essential part of arc flash safety. Workers should be trained on the hazards of arc flash, the use of PPE, and safe work practices. Regular refresher training should be provided to ensure that workers stay up to date on the latest safety procedures. Compliance with arc flash safety standards such as National Fire Protection Association or NFPA 70E is mandatory in many jurisdictions. By implementing arc flash safety measures, you can protect workers from the serious hazards of arc flash. Finally, always prioritize safety when working with electricity. Electricity can be dangerous, and it is essential to follow safe work practices to prevent accidents. If you are not qualified to work on electrical equipment, do not attempt to do so. Consult with a qualified electrician for any electrical work that needs to be done. By following these guidelines, you can help to create a safe and productive work environment.